Hello folks! This is the first class of the course entitled Materials for Photonic Applications, Glasses, Optical Fibers, and Soft Gel Materials. This course is the third internet-based course offered by Institute of Chemistry at the São Paulo State University. We will need approximately 10 weeks to introduce you to the amazing world of materials whose optical properties allow us to apply them in photonics. Pre-recorded classes like this one will be available weekly for download at the school website. Complementary information will be available as well in the form of scientific papers, videos, and some more media stuff that will allow you to follow the course, answer quizzes proposed weekly as one of the grading tools, and improve integration among participants from different cities. So let's start. Good work! The São Paulo State University was created in 1976, consolidating a project joining scientific, technological, economic, cultural, and social development committed to democratic principles and clearly conscious of its status of a governmental institution, inserted and highly active in Brazilian society. UNESP's actions are focused in nearly every field of experimental and theoretical sciences, such as engineering, health, communication, humanities, social sciences, and arts, among others. UNESP is one of the largest and most important Brazilian universities, with distinguished achievements in teaching, research, and extension services. UNESP is supported by state funds, and along with USP and Unicamp, UNESP offers free public higher education in São Paulo state. UNESP is the most successful model of a multi-campus university in Brazil. Such unique characteristic allows intense and diversified activities in the state of São Paulo. Its influence can be recognized by the level of regional development, where its campuses are located, one in the state capital and 23 others strategically distributed throughout the state. For the development of its main activities, UNESCO receives financial aid from the main research supporting agencies in the country, such as FAPESP, CNPq, CAPES, and FINEP. These resources are guaranteed by agreements that allow faculty members and students to participate in exchange programs, development of academic projects, and services. These agreements are signed with national and foreign universities, institutes, associations, foundations, city halls, government bureaus, ministries, federal and state agencies, and private companies, adding up to 300 partnerships that increase annually. The Institute of Chemistry is located in the Araraquara campus, in the heart of the São Paulo state, 270 kilometers from São Paulo city. Araraquara is an important agribusiness center, based mainly on industry, orange and sugarcane production. Since 1961, as one of the São Paulo State Research Institutes, and making part of the UNESP since its creation in 1976, the Institute of Chemistry offers free chemistry undergraduate and graduate courses. Beginning in 2013, we offer chemical engineering course as well. Research covers all main topics in chemistry and biochemistry, with innovative projects being developed in basic and applied interdisciplinary areas. Approximately 500 graduate and 1,000 undergraduate students, postdocs, and 90 researchers professors participate in the chemistry program that combines theory and exciting practice in modern and well-equipped laboratories. Our particular infrastructure composes two main labs, the Laboratory of Photonic Materials under my supervision and the Laboratory of Special Glasses under supervision of Professor Marcelo Nalim. Professor Yunus Mesadek and Professor Edson Pecoraro are also responsible for some of the ongoing research projects. In general, we are mainly devoted to material for photonics and biomaterials. Approximately 40 people work in our labs today, including undergrad, grad, and postdocs. After a while, Professor Messadec is also working at University Laval in Quebec, Canada, and for that we took advantage of the situation to propose and establish a joint international research unit between UNESP in Brazil and Laval in Canada. The idea is to establish an original international platform in order to improve collaborative work, common diploma, co-tutel thesis, exchange of undergrad and grad students, common online courses, sharing of intellectual property, and entrepreneurship formation. For those who want to know more about that, please contact us. Ongoing research projects cover different areas of interest, as health, where we study luminescent markers for imaging and diagnostics, temporary substitutes for the skin, and templates for bone regeneration. Agriculture, where fiber optic sensors for nutrients are prepared, encapsulation of nutrients, slow delivery. Telecom and information, where optical fibers are studied together with other forms of waveguides. Environment, where optical fiber sensors are also used, and materials for solar energy. And of course, education, with science diffusion, technology transfer, and the creation of spin-off companies. So let's start with our course. The tentative program to be covered include glasses, glass ceramics, waveguides, optical fibers, thin films, and channel waveguides, spontaneous and stimulated emission in lanthanide-containing materials, where we will cover the fundamentals of lanthanide spectroscopy and applications, including luminescent markers, luminophores, lasers, and optical amplifiers. After that, we will explore the soft chemistry principles involved in the so-called sol-gel methodology that allows incorporating organics in inorganic hosts. The organic-inorganic hybrids concept, where the best of both the organic and inorganic worlds are considered, will be explored. We will finish with principles of biomimicking and fundamentals of self-organization in the preparation of photonic materials. Nature is always our main inspiration source. Of course, this program is not closed. Individual interests of each one of you can also be considered. For that, we kindly ask you to suggest topics to be included. You may be asking yourselves, what does a Escher painting do here? There is no special reason for that. I simply like Escher very much. We can start by defining what photonics is. Photonics is the science of using photons as information carriers. Using photons to carry information is not a new idea. Alexander Graham Bell is better known by the invention of the telephone. However, 2 years after the telephone, he invented the photophone, which he called radiophone at the beginning. He used the sun to carry information. In the photophone, sunlight is modulated by a membrane which vibrates because of the sound behind it. At that time, the photosensitivity properties of selenium crystals were well known. The electrical conductivity of selenium crystals change when it's illuminated. Therefore, light modulated by the membrane impinging on the selenium photodetector could be translated to an electronic signal and sent to a headphone. Graham Bell succeeded in this way to send his voice to his assistant Charles Tainter, who was around 200 meters away. Bell died saying that the photophone was his greatest idea. In fact, the photophone is the base of what we call today telecommunications. With respect to the Graham Bell's device, in telecom we use lasers as light sources instead of the sun, optical fibers as light guides instead of air, quartz crystals to modulate light instead of the membrane, and more efficient detectors working in different regions of the electromagnetic spectrum. We used to say that as the 20th century was the century of electronics, the 21st century is the century of photonics, where light plays an essential role. By the way, I think you all know that in 2015 we are celebrating the International Year of Light, don't you? In order to the photophone to be practical, we had to wait more than 80 years after the Graham Bell proposition. Important contributions to that were made in the 60s, including the invention of lasers in 1960, particularly those made of semiconductors, and the proposition of Cow and Rockham in 66 that silica fibers could guide light. The experimental achievement of that came in the 80s with the preparation of high-purity silica and fibers with the lowest loss theoretically predicted of 0.2 dB per kilometer. In the material available at this course website, you will find as a gift the article Graham Bell published in 1880, entitled On the Production and Reproduction of Sound by Light. For the sake of curiosity, these three gentlemen shared the Physics Nobel Prize of 29 for their ideas and contributions that are at the heart of the optimization of the Graham Bell's photophone. We can go even further in time to find out that new materials perhaps are not that new. This is the famous Lycurgus cup, a beautiful cup made by Romans at the 4th century. It displays amazing optical properties. If seen by reflected light, it looks green. If seen by transmitted light, it looks red. The amazing properties are due to gold and silver nanoparticles present in the glass composition. If we now look at a not less beautiful Venetian cup, now we only see the red color. It is due to the presence of gold nanoparticles as well, but no green color is seen by reflected light. Of course, we know today that absorption and scattering properties of the colloidal metal particles play important role on the color we see. Roman nanoparticles were different from the Venetian ones. Romans and Venetians dominated at perfection the technique to prepare these interesting optical materials, but in fact Faraday was the first one to propose that the colors were related to the presence of the nanoparticles. Plasmonics can be considered a sub-area of photonics, studying such properties due to the metal nanoparticles. In fact, very interesting applications are being explored today by different research groups in the world. Plasmons are collective oscillations of metal surface electrons. The interesting point here is that when dealing with nanoparticles, these oscillations can be excited by visible light. For that, a gold nanoparticle suspension looks red, while a silver nanoparticle suspension looks yellow. Concerning potential applications, the excitation of surface plasmons can lead to enhancement of the local electric field a molecule will experiment at the particle's neighborhood. This enhancement of the electric field leads to enhancement of the intensity of lines in different spectroscopic techniques. The colors of the nanoparticle suspensions can be in fact tuned. In this paper, we have prepared gold-silver alloys by using pectin extracted from oranges as a stabilizer. You probably do not know, but Araraquara is one of the big orange producers in the world. Those alloys nanoparticles can find different applications from medicine to photonics. I invite you to read the paper, available at the school website, to know more details. For example, Raman spectra of some molecules on the neighborhood of a metal nanoparticle can be greatly enhanced. This is the base of SERS, that is, surface enhancement Raman scattering. In the same way, the intensity of FF transitions in lanthanide-containing materials may experiment an enhancement. This is the surface enhancement of fluorescence. SEF, SERS with two R's, holds for surface enhancement resonant Raman scattering, and SEIRA for surface enhancement of infrared absorption. By combining SERS with two R's, and special techniques used to prepare monolayers, like the Langmuir-Blodgett ones, the spectrum of a single molecule may be obtained. Awesome, isn't it? This is a very interesting and hot subject related to plasmonics. Later on in our course, we will talk about organic-inorganic hybrids. These organic-inorganic hybrids seem to be a recent subject, but it's not. This is a Maya painting. The Maya civilization extended throughout the present-day southern Mexican states of Chiapas, Tabasco, and the Yucatan Peninsula states of Quintana Roo, Campeche, and Yucatan. The Maya area also extended throughout the northern Central America region, including the present-day nations of Guatemala, Belize, western Honduras, and extreme northern El Salvador. The Maya is a Mesoamerican civilization, noted for the only known fully developed written language of the pre-Columbian Americas, as well as for its art, architecture, and mathematical and astronomical systems. Initially established during the pre-classic period, many Maya cities reached their highest state of development during the classic period, and continued throughout the post-classic period until the arrival of the Spanish. Of special interest for us here is the blue pigment Maya people utilized in their paintings. It's a very resistant to weathering, and in fact it's still there after centuries the painting was made. They prepared what is considered the first organic-inorganic hybrid, from indigo blue, an organic dye, and clay. They managed to prepare a very resistant pigment. The interesting point to be mentioned is that we still do not know exactly how Mayas prepared their blue pigment. Under the sun, the indigo blue dye itself cannot resist some wicks. If we succeed in reproducing Maya synthetic procedure, can we use the same principles to enhance resistance to weathering of, for example, OLEDs or organic solar cells? The subject is in fact very hot. In 2013, a Spanish group claimed to have discovered the Maya's recipe. They claimed to have discovered that a second yellow hydrated pigment was used together with a secret ingredient, copal resin, normally used for incense. It is worthy to read this paper and the other one the same authors published in the Journal of Mesoporous and Microporous Materials. From the next class, we will start to talk about glasses. Glasses mainly related to photonics. How a glass can be prepared, the different preparation techniques that allow us to prepare glasses from anything, the optical properties, the colors, the possibility of observing luminescence. Glass was probably the first material man learned how to prepare. There are evidences for glasses being prepared 5 centuries before Christ. As amorphous materials, they are isotropic. They are transparent, and by tuning chemical compositions, we are able to obtain transparency in different regions of the electromagnetic spectrum. The tuning of compositions and the consequent tuning of properties is possible because of the freedom to be out of any stoichiometric composition. We used to say, in fact, that you can add all the periodic table to a glass composition. Glasses are moldable. There is freedom for the shape. Glasses are mechanically resistant. They are chemically resistant as well. The solubility may in fact be tuned, which is a very important property concerning, for example, bioglasses for drug delivery. Of course, the beauty of glasses is incomparable. As we mentioned before, at the school website we will find different media stuff. These are some videos collected from the internet that you must watch, for sure. For example, how marbles, that are glass spheres, are made. Everybody has already played with one of these in his childhood. It's interesting to see how they are prepared. After that, the Corning series, entitled A Day of Glass. You must watch these three videos. Amazing. And to finish this warm-up for the course, take a look at how an optical fiber is prepared. To be sure that we will see these videos, one of the quizzes at the end of this class will involve these videos. We will explore functionality in glasses. This is a first example. The white light you see in this picture is the emission of telluride glass excited in the infrared. It contains the ions ytterbium and thulium, and the emission spectrum shows the blue and red band characteristic of thulium. The energy levels diagram shows the entire process. After absorbing one photon, there is an energy transfer from ytterbium to thulium. The successive absorption of a second and a third photons are followed by energy transfer to thulium, that at the end will be in an upper excited state. Red and blue emissions account for the white light we see. This is the so-called upconversion processes, well known for lanthanides containing materials, and that can allow several different applications for these glasses. In this second example, chalcogenide glasses are considered. Gallium germanium sulfide glasses present the interesting property of photosensitivity. Once illuminated with UV light, photoexpansion occurs in the illuminated area. Expansion will be proportional to the power of the UV light. Moreover, the expanded area will present a lower refractive index compared to the mother glass. This figure shows the refractive index profile for a glass which surface was illuminated through a mask with different UV laser power values. Lower index relates to higher laser power and larger expansion observed. Photoexpansion may be used to construct gratings at the glass surface. This AFM image shows the surface of a glass submitted to a holographic process of writing. Two beam lasers interfering on the glass surface lead to a periodic pattern of the surface. Illuminated areas will expand and a grating is formed. The third example considers oxyfluoride glasses. In this case, a glass prepared from lead germanate, cadmium fluoride, and lead fluoride. The interesting point here is that crystallization can be controlled in these glasses. Lead fluoride nanocrystals may be obtained in a way that the final material presents the same transparency of the mother glass. Lead fluoride crystals are known to present the property of superionicity, that is, above a certain temperature, fluoride ions are mobile, like in a liquid. The transition ionic-superionic can be easily detected in a conductivity measurement as a function of the temperature. This figure shows the results for such measurements for a transparent glass ceramic in this system. Results are shown in an Arrhenius plot. Ionic to superionic transition is easily identified at 125 centigrades. We call the attention for the fact that Tg for these glasses are located at much higher temperatures, around 350 degrees. At 125 degrees, the solid behaves like a liquid, in which concerns conductivity. Once doped with erbium ions, these ions will concentrate in the crystalline phase, and this is also very interesting. This figure shows erbium emission at the wavelength that is interesting for telecom purpose, that is around 1.5 micron. Spectra obtained for the mother glass and for the transparent glass ceramics are different. In fact, the spectrum obtained for the glass ceramic closely resembles the spectrum obtained for the lead fluoride crystals doped with erbium. that is, a crystal-like spectrum, is obtained for the transparent material that was obtained by conventional glass techniques. These are barium fluoride sodium phosphate tungsten oxide glasses. Several interesting points refer to the possibility of incorporating large amounts of tungsten oxide to the glass composition. This figure shows Raman spectra obtained for these glasses as a function of tungsten oxide content. Details of the assignments of the bands are not important at this moment. The main point here refers to the fact that clustering of WO6 units are evident for higher tungsten oxide contents. An important consequence of this clustering concerns absorption of light. This figure shows transmission for green light as a function of the power of incident light. For low tungsten oxide contents, things look normal. That is, there is no dependence of the transmission on the power of the incident light. However, for higher tungsten oxide contents, a nonlinear behavior is clear. Glasses absorb more and more light as the light power increases. A clear application for these glasses concerns optical limiting devices. Moreover, these glasses are very stable against crystallization, allowing easily fibering. These tungsten-based glasses also display photochromism. Irradiated areas have the color changed from yellow to blue. The process is reversible in the presence of oxygen, and depending on the wavelength of the incident laser, patterns can be written on the surface or in the bulk. So far, we have mentioned transparent glass ceramics, but glass ceramics will be in fact an entire subject that we will cover. We will deal with materials obtained from glasses, that is, by controlled crystallization of the mother glass. Glass ceramics may be obtained with properties that differ from conventional ceramics obtained by classic solid-state reactions from crystalline precursors. For example, zero-expansion materials may be obtained. These zero-expansion materials find application from kitchenware to telescope mirrors, where small variation in dimensions would be terrible. In this issue of the American Ceramic Society's Bulletin, our dear colleague Edgar Zanotto from the Federal University of São Carlos, 40 kilometers from Araraquara, published a review on these materials, also available at the school website. Of course, we will use this Edgar's review in our course. Following glass ceramics, optical waveguides will be treated. Optical fibers will be first reviewed. How are they prepared? Besides the well-known application of light guides in telecom, other applications like temperature and pressure sensors and structured fibers will be treated. Thin films, channel waveguides, and applications in integrated optics will follow. We will define stimulated and spontaneous emissions, and the fundamentals of lanthanide spectroscopy will be reviewed towards optical application of these ions in luminescent markers, luminophores, lasers, and optical amplifiers. This map from the Internet, from the Oxford Internet Institute, shows the connected world. Colors give an idea of online people. More research in communication technology is needed in order to really connect everybody. It can be taken as a driving force to researching materials for that. The other image shows connections by optical cables. We are indeed connected. This table shows the evolution of communication systems. In fact, digital signals and optical cables started operation by 1988 with the TAT-8 cable. In this table, the evolution may be followed. We may observe that optical amplification is involved only in the TAT-12 and 13 cables, capable of delivering 5 gigabits per second of bandwidth. This is the scheme of a standard telecom optical fiber. It has a core, normally in silica, with dopants to increase the refractive index, like germanium or phosphorus. The core carries the light signal. The cladding, normally made in silica, is responsible to keep the optical signal in the core, and the coating that protects the fiber and provides mechanical resistance. Silica is transparent in the visible, everybody knows that. But the visible region is not the region of the electromagnetic spectrum that silica is most transparent. In this figure, we have a typical absorption spectrum for a silica-based glass. All dielectric material shows this V-type absorption curve. Observe that the ordinates axis giving absorption coefficient is given in a logarithmic scale. Changes of 12 orders of magnitude are shown. It's a huge change. In the high energy part of the spectrum, absorption is due to electronic transitions from the valence band to the conduction band. The position of the absorption edge will depend on the energy gap of the material and will be given by the so-called Urbach tail. In the low energy side, increasing absorption is due to the harmonics of the fundamental vibrational modes. In solid-state physics, vibrational modes are extended and are called phonons. Therefore, the increase in the absorption coefficient due to the multiples of the fundamental phonon is called multiphonon absorption edge. Both high energy and low energy absorption coefficients will define the region of minimum absorption. The chemical nature of the material will then define the region of minimum absorption. For silica, that minimum is at 1.54 microns in the infrared. This is again the absorption spectrum obtained for silica. Just the region of minimum absorption is shown. We have in the left the unit used to describe attenuation in optical systems, the decibel or dB. We see that dB is related to the unit absorbance that we are more used to in our chemistry labs. In the figure, we see that in our absorbance units, the attenuation for silica fibers in the visible part of the spectrum is around 5 times 10 to the minus 5 for an optical path of 1 cm, a commercial cuvette, for example. Silica is indeed transparent in the visible. In our spectrophotometers, we do not have the precision to read such a small value of absorbance. As already said, this is not the region where silica is most transparent. In the infrared, 1.5 microns, the absorbance for 1 cm optical path would be 10 to the minus 7. These values are calculated for a 1 cm optical path. If we perform the same calculation for 1 km optical path, absorbance would be 0.01. This means that 96% of transmission would be observed. The conclusion of this observation is that for long optical paths, silica is not completely transparent. Even at 1.5 microns, light will be attenuated. This figure shows another interesting aspect related to the optical attenuation in optical fibers. It concerns our ability to purify the chemicals we use. It shows that at the time of Egyptians, 5,000 years ago, silica was mostly opaque. What we call optical glasses started to appear by the 20th century. As we said before, telecommunications based on optical fibers could be possible only after high-purity silica could be obtained, and that happened in the 70s. The minimum attenuation possible was obtained by the 80s. At this point, we can mention optical amplifiers. We have already mentioned that the effective utilization of optical amplifiers started around 1996, what could be considered a revolution in telecommunications. The principle for optical amplifiers is the same of the laser, that is, stimulated emission. The difference is that here we do not have an optical cavity. An active ion, a lanthanide in general, is kept in the excited state by a given pumping mechanism. The attenuated signal will trigger the emission of a second photon by stimulated emission. The second photon added to the signal will provide the so-called optical amplification. Erbium emits at exactly 1.54 microns, and for that it's used in modern telecom networks. EDFA, erbium-doped fiber amplifiers, are used all over the world in optical amplifiers. We will see that fibers can be very different from the standard core cladding configuration. Photonic bandgap fibers may present the configuration of the figure, that is, longitudinal holes are present in the fiber's structure. In fact, optical properties of such a fiber can be controlled by the number, dimensions, and geometry of the holes. A new and exciting field of research has grown for these materials. Different geometries are possible. Light may be guided in a solid core or in a hollow core, like the one of the figure. This review from 2006 shows the main properties of these hollow core fibers. In the preparation of such fibers, silica capillaries are needed first. Assembling of the capillaries and drawing under pressure are the next steps to be performed. Few laboratories in the world dominate that procedure, and for that these fibers are very expensive. Very interesting news appeared in 2013. As is well known, light propagates at different speeds in different materials. In fact, the ratio of the light speed in vacuum to the speed in a given material defines what we call refractive index. The speed of the light is for that 31% slower in silica glass than in vacuum. Researchers of Southampton in UK have published in Nature Photonics some enlightening results. They reported a fundamentally improved hollow core photonic bandgap fiber that provides a record combination of low loss and wide bandwidth. They used the fiber to transmit 37 40 gigabits per second channels at a 1.54 microsecond per kilometer faster speed than in a conventional fiber. This represents the first experimental demonstration of fiber-based wavelength division multiplexed data transmission at close to the speed of light in vacuum. The value achieved is in fact 99.7% of the speed of light in vacuum. This paper is also available at the school website. This is a figure from the paper. At the top, the image shows the cross-section of the PBG photonic bandgap fiber. The hollow core is easily seen. Together with this image, authors show the cutback loss of their fiber in red in comparison with the best results from literature in blue. The spectral extension of the optical telecommunications S, C, and L bands is also shown. In B, authors show the transmission window for 5 meters of fiber, obtained by changing the experimental conditions, mainly pressure, of the fiber preparation. In C, the relative contribution of light confinement and scattering to the total calculated loss. The main contribution comes from surface scattering. PBG materials can be prepared in 1, 2, or 3 dimensions. 2D and 3D PBG materials, shown in the figure, are obtained by using templates. For 2D PBG, photoresist and lithography methods are used. For 3D PBG, polymer spheres organized in a colloidal crystal are used as templates. These are some materials obtained in our lab by using latex spheres. Latex spheres are prepared in a way that dispersion in sizes is low. Centrifugation of the latex suspension leads to pieces of material displaying a crystalline organization for the spheres. Since the size of the spheres is of the order of the size of the wavelength of visible light, colors can be seen at the surface of the material. The colors you see are in fact the results of Bragg diffraction of visible light by the colloidal crystal. This is a latex opal. Concerning PBG concepts, seeing the color red in a given direction of observation means that red color cannot propagate into the material in that direction. We say that there is a photonic band gap for red color in that direction. If the red color could be seen in any direction of observation, we could claim a total photonic band gap for red color. This would be a real photonic crystal. This is not the case for this material. The photonic band gap for red color appears in just one direction. We say that this is a pseudo band gap. The plot shows reflection spectra obtained at different angles of observation. The peak corresponds to diffraction. We can conclude for that since there is a shift as a function of the angle, obeying therefore the Bragg law of diffraction. Two-dimensional photonic crystal layers may be obtained by combining holograph recording and evaporation of antimony-based glasses. Photoresist templates are first prepared by holographic methods as shown in this figure. The photoresist is first deposited on a borosilicate glass substrate by spin coating. After that, the photoresist is submitted to a double exposure of two beam interference patterns by using a 457 nanometers laser. Then, the photoresist is developed, followed by the deposition of the antimony-based glasses by electron beam-assisted evaporation. In the final step, the photoresist is removed. Different structures may be obtained by double exposition at different angles, as shown in these two figures. These figures show the templates incorporated with antimony sulfide antimony oxide-based glasses by evaporation. The final PC is obtained after removing the templates. Such materials present high refractive index that can be tuned from 1.8 to 2.4 depending on the film composition, the ratio sulfide to oxide. The good quality of the obtained samples allowed the measurement of their PC properties through the well-defined funnel resonances that appear in the transmittance spectrum measurements at different incidence angles, as shown in the figure. The experimental results are in good agreement with the calculated band diagram for the hexagonal asymmetric structure. A final topic to be cited in this introductory section concerns the soft chemistry principles involved in what we call the sol-gel methodology. These relatively low temperature methods allow obtaining glass or ceramics compositions impossible to be obtained by conventional methods. For example, thin films with composition zirconia alumina. These high-temperature oxides are difficult to be evaporated. However, by sol-gel, they are easily obtained. Even organics may be incorporated in an inorganic host, or alternatively, inorganic nanoparticles can be added to organic hosts. In this case, solid-state properties of the nanoparticles can add interesting functionalities to the materials. In these cases, we are talking about organic-inorganic hybrids. These organic-inorganic materials gather the good things of both worlds, the organic and the inorganic, in a single material that can be considered a composite at the molecular level. The interesting point to be cited is the fact that the synergy between both phases can bring additional properties to the material, not observed in the individual components. We used to say that new properties emerge from the synergistic effects. Very interesting applications are possible in photonics as active layers, sensors, and optoelectronic devices. We will also talk about mimicking nature. When we look at nature, we see amazing photonic structures. For example, consider this butterfly, easily found in Brazil. It looks blue, but there is no blue pigment in these wings. The color is in fact the result of the Bragg diffraction of the visible light due to the structure of the wings. This can be easily checked by observing these wings under two different kinds of illumination, from the top or from the back. The photonic structure of the wings of these wonderful butterflies may be observed under the microscope. Butterflies are in fact the source of inspiration of different photonic devices. In this book, written in French, called Photonique des Morphos, and in this review paper published in Energy and Environment Science, you will find a lot of information in order to develop new photonic materials by mimicking nature structures. The versatility of the sol-gel process can be summarized in this scheme. The starting point is a solution, a metal or semi-metal alkoxide, or a salt solution. From the initial solution, the controlled hydrolysis and condensation reactions lead to a stable sol, that is, a stable suspension of colloidal particles. Let us call your attention to the fact that the chemical nature, size, and morphology of these colloidal particles can be in fact controlled by the experimental conditions, like pH, catalysts, and temperature. And this is the strength of the sol-gel processes. The properties of the final material can be tuned from the precursor nanoparticles. Coming back to the scheme, from the stable sol, different materials may be obtained. A substrate can be coated by spin or deep coating, for example. The dried film is called a xerogel, a word with Greek origins meaning dried. This xerogel film can be densified by thermal or photo treatments, leading to dense films. From the sol, a gel may be obtained, where gel means a 3D stable solid made of colloidal particles interconnected and expanded in a liquid medium. Depending on the drying conditions, we can get different materials. Freeze-drying processes involving low temperatures and pressures will give cryogels. Ordinary drying methods involving ordinary or low pressures and temperature will give xerogels. And finally, the drying can be performed under supercritical conditions, high pressures and temperatures, leading to the so-called aerogels. Alternatively, particles may be obtained. The precipitation conditions may be controlled in a way that we obtain at the end a monodispersed collection of particles with morphology controlled as well. No other method allows such control. Even fibers may be obtained in a kind of extrusion method, well dominated in the field of polymers. These are the two main references in this area. The first one is the famous book from Brinker and Scherer. It's a kind of Bible of the area. Everything is in there. The second one is one of the main journals of the area. The Journal of Sol-Gel Science and Technology brings interesting papers, and many of them will be used for sure in this course. These are the main reactions involved in the sol-gel process. From the starting metal oxide solution, controlled hydrolysis lead to the sol. Condensation reactions among colloidal particles lead to the gel, which can be treated leading to glasses, ceramics, or hybrids. Depending on the conditions, completely different materials can be obtained. Catalysis, for example, can be performed in acidic or basic solutions. In the case of acid catalyzed reactions, linear or randomly branched polymeric structure are obtained. Materials obtained in this way will present in general good optical quality and porosity at the molecular level. Materials for photonics, like preforms or thin films, can be obtained in such conditions. On the other hand, base catalyzed reactions will lead to highly branched clusters. Particles are instead obtained. Dense submicronic particles of silica are obtained in the well-known Stauber method. This collection of monodisperse spheres can be used, for example, in order to obtain an opaline structure, displaying iridescence. By the way, natural opals are colloidal crystals of silica spheres. The beautiful optical effects are also due to the Bragg diffraction of visible light. Brazilian opals are amongst the most beautiful in the world. We have already mentioned Faraday in this introductory class. His work on gold nanoparticle suspensions can be in fact considered the starting point of the science of colloids, where the sol-gel method may be included. This scheme, carefully prepared by our dear colleague Lubomir Spanel, today working in Rennes, France, shows the main characteristic of colloidal particles. You can observe the three different abscissa axes, showing molar mass, size, and surface area. For the sake of comparison, relative increased dimensions are shown for atoms, molecules, proteins, polymers, virus, DNA, vesicles, and macroscopic solids. Colloids include clusters, nanoparticles, and microparticles. You can see that the colloidal domain is the domain we use to call today nanotechnology. In fact, we have an advice for you. If you are submitting a research project to any funding agency, please use the keyword nanotechnology. Otherwise, you'll have no money. It's a joke, of course. This scheme, also prepared by Spanel, shows the analytical methods normally used in colloidal science. Particle sizes and colloidal growth are studied by photon correlation spectroscopy, (PCS), also called dynamic light scattering or quasi-elastic light scattering. We use this technique to determine the size distribution profile of nanoparticles or polymers in suspension. Ultraviolet visible spectroscopy, luminescence, confocal optical microscopy are other techniques that can give us information at the nanometric scale. Pulse radiolysis and laser photolysis are high-energy techniques used in the production of nanoparticles by the so-called top-down approach. The structure of aggregates, the chemistry at the interface, and nanocrystallinity may be explored by scattering techniques like small angles X-ray scattering, small angles neutrons scattering, and wide angle X-ray scattering, besides X-rays diffraction. Electron microscopy techniques like high-resolution transmission electron microscopy, scanning electron microscopy, scanning tunneling microscopy, atomic force microscopy are well used in the study of nanoparticles, together with X-rays photoelectrons spectroscopy. Particle sizes, surface area, and zeta potential are studied by nitrogen adsorption, ultracentrifugation, and electrophoresis. If Faraday's work is considered a starting point for colloidal science, with no doubt Richard Feynman is considered the father of nanotechnology. From his famous speech when receiving the Physics Nobel Prize in 1959 come his prophetic words that are present in all textbooks on nanotechnology. There is plenty of room at the bottom. In fact, he initiated the development of new thin film technologies combined with top-down approach to nanoparticles preparation. We used to say that the bottom limit for those techniques are around 10 nanometers. Important contributions came also from chemistry. These guys, Afros, Bruss, and Hingling, developed the chemical bottom-up approach to the nanoparticles. The quantum size effect, important to understand the optical properties of semiconductor nanoparticles, was also developed. We will see that organic and inorganic hybrids occupy a special place in this more general colloidal science. For example, tin oxide nanoparticles containing europium ions can be dispersed in water and can be modified at the surface with beta diketonates. By doing that, we obtained water-soluble nanoparticles displaying strong luminescence under UV excitation. These particles can find important applications in photonics. Another interesting example to mention at this moment would be the so-called ureazyls. These materials get this name from their chemical structure, where an urea bridge connects the organic and inorganic parts of the material. These ureazyl hybrids are luminescent under UV excitation, and the position of the broad emission band can be tuned by the molecular local structure. Hybrids may be also photopolymerizable. This is a very important property concerning materials processing. Today, one can easily find modified alkoxides to buy, like these acrylate or epoxy silanes. Holographic techniques may be used to selectively polymerize thin films. By using a simple experimental setup, a Lloyd mirror, a grating can be engraved at the surface of a material. In this paper, we have prepared different structures on organic and inorganic photosensitive hybrids. The paper is available at the school website for more details. With this, we finish our first class. Let's end up this first class with this beautiful Roman photonic cup. Again, it will serve as inspiration source for all of us. We leave you with some questions for you to think about for the next week. There are some definitions for glasses found in chemistry textbooks. Which one is correct? We leave you with these beautiful images of Iguaçu Falls, one of the beauties of our country, located at the triple frontier among Brazil, Argentina, and Paraguay. This is one of those places we absolutely need to see before dying. See you next class. Do not forget to download the first quizzes list available at our website.